been circulating a little bit in the astronomy community. We've rewritten the words to Twinkle, Twinkle, Little Star. It's no longer Twinkle, Twinkle, Little Star, how I wonder what you are. It's Twinkle, Twinkle, Little Star, I know exactly what you are. And it goes on. There's a number of verses, there's a number of different versions. But the idea is that astronomers don't need to wonder what a star is made of anymore. We know. We know exactly what stars are made of. We know exactly how they work. They're not a problem in astronomy anymore because we understand them. And I'm here today to convince you that that's wrong. So part of the reason that we think this way, that we think we know so much about stars, is because we know so much about our sun. So this plot behind me shows a model of the sun compared to the sun. And if our model was completely 100% right, you would have a flat line at 0. And we don't. But if you look at the scale, the differences are tiny. The differences between our models of the sun and the way the sun actually works are less than 0.5%. This is a really, really accurate model. We understand the sun really, really well. Now, the sun, from my perspective, is actually a very easy star to understand. If you look at the star, it's spherical. That means that from the physics perspective, from the mathematical perspective, it's a one-dimensional problem. You can solve the sun, and all you need to know is the radius. If you can find the radius, it doesn't matter how close you are to the pole, how close you are to the equator, what your equivalent of longitude is on the sun. All you need to know is the radius. And that means that solving the sun is a fairly simple problem. And I would be willing to bet that your cell phone has enough computational power to be able to calculate a model of the sun in a matter of minutes. It goes very quickly. It's very simple mathematically. Now, unfortunately, that doesn't work when we start applying this to other stars. When we start looking at other stars, we start finding all kinds of other issues that don't apply to the sun. And that's what I'm here to talk about today, is these other issues. And you might be wondering, why do we ignore these other issues? Why don't we take them into account? Well, the answer is they're hard. They're often multidimensional. They don't let us just do things as a function of radius anymore. So the first issue is one that is near and dear to my heart. I'm going to talk about rotation, because that's what I study. Now, the sun rotates about every 26 days. It goes around once. If you work that out, that gives you a speed at the equator of 2 kilometers per second. Now, 2 kilometers per second here on Earth seems really fast. But in astronomical terms, it's slow. It's really slow. This particular star, this is Altair. It's rapidly rotating. It's a typical rapidly rotating star. And these stars can have velocities at the surface of hundreds of kilometers per second. So not 2 kilometers per second, hundreds of kilometers per second. And when that happens, when you have a star rotating this rapidly, then you start to get flattening. Like somebody mentioned earlier today, you get what's called an oblate spheroid. The analogy is if you're spinning pizza dough, you start with a ball of dough, you spin it long enough, and it flattens out into a disk. Stars don't go quite that far, but they do flatten out. They get larger at the equator and smaller at the poles. They're no longer a one-dimensional problem. You now have to solve them in 2 dimensions. Another problem with this type of star is the temperature. Because of this variation in surface, with the pole being smaller, the pole is now hotter and brighter than the equator, which looks cooler and dimmer. And so what you see when you look at this star depends on whether you're looking at the pole or whether you're looking at the equator. The next issue I want to talk about is convection. Convection is a heat transfer process. If you heat fluid, little bits of the fluid start to rise, and they transfer heat, they carry it up to a cooler layer, dump their heat, and then sink back down again. If you want to model convection, it's intrinsically a 3-dimensional process. There's no way around that. You have to model convection in 3 dimensions to get it really accurately. But we can make approximations. Because stars, we like to treat stars as one-dimensional problems, we like to have approximations for convection that are one-dimensional. And the one we use most often is called mixing length. And the mixing length would be the height that one of these blobs rises in the star. The only way we have to calibrate that process is by matching our models to the sun. And so that's what we do, and then we apply that to other stars. But we really have no way of knowing if that's what mixing length really should be in these other stars. And so that's a big problem. A related issue is something we call convective overshoot. Now, if you have all of these motions, this heat transfer, it's like huge cycles going inside the star. The stuff that's moving around, we can calculate where it should be moving. So we can say at 0.7 solar radii, we expect there to be a boundary. And above that boundary, stuff should be convective, it should be moving, and below that, it shouldn't. But the problem is, when the stuff is moving, it doesn't respect that boundary, because that boundary only exists in our models. In the star itself, the stuff is moving, and so when it gets to the boundary, it might not get pushed anymore, but it's still moving, so it's going to keep going a little bit. It's going to overshoot that boundary. And we don't know how far this goes. We don't know how big this parameter should be. We don't know how much extra mixing this produces. It might vary from star to star. It might vary within a star, and we just don't know. But it does matter. This plot shows two different stars, one shown with a solid line, does have convective overshooting, and the stars shown with the dashed lines don't. And so you can see that this makes a difference in the way stars evolve. This makes a difference in the way stars behave. Another issue is magnetic fields. This one gets ignored a lot because up until a few years ago we couldn't measure magnetic fields in other stars. But now we can, and we can produce models of what those magnetic fields look like. And we can produce models of what those magnetic fields do right at the surface. But nobody, none of the astronomers in the world try and model stellar evolution, including magnetic fields. So we have no idea what effect this is going to have. Another issue is the fact that most stars are actually binary stars. Our sun seems to be kind of unusual. A binary star, there's going to be gravitational attraction between the two stars, and so instead of having a nice spherical object, they're now going to be pulled towards each other a little bit. So each star is going to be a little bit elongated in the direction of its companion. Now again, you no longer have a one-dimensional problem. It's a two-dimensional problem, maybe even a three-dimensional problem. And there are all kinds of other complications with binaries as well. The stars can start to transfer matter back and forth between them. We're not quite sure exactly what effect this has. Eventually, the stars might end up sharing an envelope, so both of the stars are inside one big cloud of gas. And this is extremely difficult to model. It's a three-dimensional process. It's got very short timescales and very long timescales, and we just don't know how it works. Another area where I work is in the luminous blue variables. And these are an entire class of stars. This is not a process. This is an entire class of stars that we don't understand. This is the most famous example. It's called Eta Carina. Eta Carina is at the center of this big white nebula. And when astronomers back in the 1840s observed Eta Carina, and they discovered that it got brighter. They were watching it, and it got brighter and brighter until for a while it was the brightest object in the sky. And then it dimmed away again, and they actually lost sight of it. And when we went and looked at it many years later, we saw this nebula around it, this big cloud of white gas. We can trace that material back, and we can figure out that at this point when Eta Carina got so much brighter in the 1840s, it ejected this nebula, which contains 10 times the mass of the sun. This is a huge star to start with, and it's lost a whole bunch of material, and we don't know why. Again, you can see this is clearly a non-spherical process. So if you want to model this, you have to go beyond one dimension. But we have to figure out what to model first. We don't know how these stars fit in as an evolution sequence either. They don't show up in our models. They just don't exist as far as the theory is concerned. So why should we care about all these things? I mean, stars, the one-dimensional model works well enough for a lot of stars. Why should we care about all these extra details? Well, it turns out that stellar astrophysics influences a lot of other areas in astronomy. It has a lot of other effects. One of the effects is on planet hunting. This is a big hot topic in astronomy lately. People have spent a lot of time looking for Earth-like planets around other stars. And they've been finding them, which is really exciting. And this is the most common way they find them these days. It's called the planet transit method. And what happens is the planet goes in front of the star and blocks out a little bit of the light. And when it does that, you see a little bit of a dip in the light curve from the star, if you watch the star over time. Now, the size and shape of this dip tell you a lot of information about the planet. You can determine things like the radius of the planet, for example. But what you get is all this information about the planet relative to the size of the star. So you may think you're measuring your planet really accurately, but if you don't know the details of your star, if you don't know how big your star is, you're going to have a lot of uncertainty on the size of your planet. And so to get really good information about planets, we need to know about stars. Another place that is a really important, the stars have a really important effect, is on galaxies, which is no surprise, right? Stars are made of galaxies. The Milky Way, for example, has about 100 billion stars in it. And so when people want to model galaxies, what they do is they take models of stars and they add up the models of about 100 billion stars and say this is what the light from a galaxy should look like. But that is only going to be as good as the stellar models that go in. Now, they determine a lot of information from this. In the top left over here, you can see the black curve is one of these models of what we think a galaxy should look like. And the points are data, so it's a fit to the model. The model is a fit to the data, sorry. And we use this to determine the age of the galaxy, and the mass of the galaxy, and how fast the galaxy is forming stars. These are essential things to understand star formation histories, the formation of structure in the universe. It's all kinds of really important things that we need to understand. And this is an area where they've shown, for sure, that it matters. So this bottom plot here shows, the black shows a model of a galaxy. So you take a galaxy, you take a bunch of stars, model the galaxy, and you get the black curve. And one of the types of stars that's included in this black curve is something called an asymptotic giant branch star. Type of star is not terribly important. But what is important is that these stars undergo what we call thermal pulses. And it's a very short phase, and so they ignored it for a long time. Until about 2005, a group said, well, what happens if we include this short-lived thermal pulse phase? And when they did that in these models, they got the red curve, which you can see is very different. So if you try and fit a galaxy using the red curve, you're going to get very different results. And who knows what effects we're going to get if we start adding in some of these other factors that I have talked about, some of these other issues. So the theme of today's conference has been to think outside the box. And I'd like to end by showing you a type of model that we call star in a box in astronomy. What we do is, instead of modeling in one dimension, we actually do model in 3 dimensions. Put the star inside of a box so you can model the whole thing. This is a model of Betelgeuse, which is the star in Orion's shoulder. And you can see it starts to get a little bit non-spherical. The weird lines you see are the effects of convection. So we're starting to factor in some of these effects that I've said were generally neglected in astronomy. And so, in conclusion, I think I'd like to say that in astronomy, or in stellar astrophysics at least, we really need to start thinking outside the box by putting the star back in. Thank you.